As a quick review from Chem 221, the model of the atom that's used right now, atoms are basically like small spheres. And most of the area of the atom is taken up by where the electrons, if you will, circle around. And we talked about in Chem 221 how they don't really circle. There's probabilities and orbitals and all that kind of stuff. But the important part is that the electrons take up most of the volume. And in the very, very center, more or less, of the atom is the nucleus, which is a very, very small volume. But in that volume, you actually have most of the mass. Most of the mass of the atom comes from protons and neutrons, and that's where they're stored in the nucleus. So you've got this hyper small little nucleus with almost all the mass. The density of the nucleus is way off the charts compared to anything we're used to in our regular world, electrons around the outside, et cetera, et cetera. Now, because those protons and neutrons are so tightly bound in that small amount of volume, the energy required to keep them there is fantastic. All right, it's way above the normal kind of energies we've been used to in Chemistry 221 and Chemistry 222. So the reactions we're going to look at are generally much higher in energy than the reactions we've seen so far for acids and bases and sodium reacting with metal, stuff like that. When you get down to the nuclear level, then man, the energies are quite different. So think about that in the back of your mind. Some of the heroes and the pioneers, if you will, of nuclear chemistry or the areas of the nucleus include, of course, my beloved Marie Curie, who we talked about in Chem 221. Her husband, Pierre, was also an explorer, and Henry Becquerel. Henry Becquerel was the one that coined the term radiation because there were rays emanating somehow from these samples, et cetera, et cetera. They didn't understand the power of the nucleus, and with power comes danger, and that caused some bad results. So like poor Marie Curie died of leukemia, stuff like that. But there is a lot of potential. Power is an interesting thing. In the wrong, attitude, it can do bad things, but in the right things, you can do some really cool things with it. So my goal in this chapter is also to let you know that there is a lot of really cool kind of potential for nuclear reactions. And there's yays and nays with everything, and we'll talk about those too as we go through this section. On the periodic table, another thing to review is that all periodic tables have at a minimum the atomic number, the symbol, and the atomic weight. Well, they'll have those three at a minimum if they're like a real science periodic table. If they're one of the ones that hangs in your shower as a shower curtain, maybe not. But anyway, I digress. The important part for us now is not if your periodic table on the shower curtain is legit or not. But what is important is I want to remind you what the atomic number means. And the atomic number gets the symbol Z, and Z represents the number of protons in the nucleus, all right? And that's really important. If you change the number of protons, you change the atom itself. So like aluminum right there has an atomic number 13, so that means 13 protons. If you take away one of those protons, the atomic number would become 12. And on the periodic table, number 12 is magnesium. So you change the protons, you change the element itself. Now you can take or add electrons to make them positive or negative ions, stuff like that. But you don't change the number of protons without actually changing the element itself. You can change the number of neutrons as well, and that creates isotopes, which we talked about in Chem 221. So as an example of a boron atom, boron always has 5 protons because that's the atomic number. And if you add 5 neutrons into the mix, then you have a mass number, which gets the symbol A mass number of 10. And the symbolism that's used sometimes for these things is shown right here. The upper left-hand corner is the mass number, the lower left-hand number is the atomic number, and the atomic number and the symbol, of course, go really well together. Now, if you had, instead of 5 neutrons, you had 6 neutrons in boron, you'd still have 5 protons plus 6 neutrons, you'd have a mass number of 11. So boron 11, which is also referenced right here, is just another isotope of boron. And you would write a boron 11 with a superscript 11 instead of 10. The atomic number is still 5. The symbol is still B. So this is how you would write different isotopes. So you change the number of electrons in an atom, you make it positive or negative ions. You change the number of neutrons, then you'd have a different isotope. But if you change the number of protons, then you actually change the element itself. Okay, so this is a question that's a quick review from Chem 221. It says copper can be found as two primary isotopes, copper 63 and copper 65. Notice that the little superscript is usually listed after the name, so copper 63 would be 63Cu, etc., etc. Anyway, which isotope is more abundant? And it lists the two isotopes and says more information is necessary. This is a good time to get out a periodic table. And again, the periodic table I recommend is at mhchem.org/per-tab. But honestly, for this question, you can use just about any periodic table you want to. And what you need to look at here, first of all, find copper on the periodic table, and it's number 29. So that means there's 29 protons in copper. But what the number you need is the other number, 63.546. And 63.546 is the molar mass of copper. So if you have 63.546 grams of copper, you have a mole of copper. But if you remember back from Chem 221, that number is a statistical average of the isotopes of copper. And so in this problem, for example, you can literally write like a type of a number line. And I'm going to make a very cheesy one here. And again, I apologize because I am not an artist. But anyway, I wrote up there 63 and 65. And of course, that corresponds to the 63 copper and the 65 copper. Now, on a number line, halfway would be 64. And how this all works out is I'm going to look at that periodic table number again for copper, and it was 63.546. So roughly, all right, I'm going to make a little dashed line right there. Roughly, and again, my line isn't even straight. It's very embarrassing. So anyway, 63.546 would be roughly halfway between 63 and 64. The molar mass gives you a hint as to which isotope is most abundant, because remembering that the two isotopes together equal the molar mass on the periodic table, you can kind of see what's happening. For example, if you had 50% copper 63 and 50% copper 65, then the average of those two would be halfway between 63 and 65, which would be 64. All right. So if the number on the periodic table was 64, then you'd say you had 50% 63 and 50% 65. But again, the number on the periodic table there is 63.546. All right. That's a terrible 3. Anyway, 63.546. And 63.546 is certainly closer to 63 than it is to 65. And that must mean then that copper 63 is more abundant. And in Chem 221, we did a problem where we actually calculated the percentages. And if I recall correctly, copper 63 was about 70% of all copper, and copper 65 was about 30%. You can look these numbers up on Google to see that that's about what it is, all right? But the important part is that the molar mass gave you a hint as to which was the more abundant isotope. And in this case, it's certainly copper 63. In this section, because the energies are so much higher when we're talking about the nucleus, we're going to run into some special particles, quote unquote. One of these technically isn't a particle, but the other ones certainly are. And these are going to be very unique to nuclear chemistry. They're things we really haven't had to talk about, at least in this context, up until this point. So these are going to be things that are going to pop up in the upcoming lecture, so just get ready. The first of them is nothing more technically than a helium nucleus. Now, notice the symbol, especially on the left-hand side right there. If you have helium, then you have an atomic number 2, and the dominant isotope of helium is helium-4. If you look on the periodic table for helium, the molar mass 4.003, that's really, really close to 4. So you would think at first, if you wrote this normally, 4,2 helium like that, it would be regular helium, the kind of helium where if you're at a birthday party, you can open the balloon and then you tackle like a chipmunk. But of course, I've never done that before. Okay, really, I have. But anyway, I digress. Normal helium is one thing. All right, it's cool for doing balloons, and you can use super cold things with liquid helium. This is not that kind of helium. We're talking in this thing about an alpha particle. And you can imagine this is helium on steroids. It like can't stop. It's super high energy. If you were to like have a balloon of alpha particles, and that'd be scary by the way, but if you did and you sucked them up like that, you'd be dead, because alpha particles we're going to see are super high energy. They're very reactive, and in your body they would cause a lot of damage. So an alpha particle, I mean, really is just a helium. All right. Technically, the alpha particle probably doesn't have any electrons because it's so high energy, it pushes the electrons away. So you've got this super positively charged helium nucleus. This is pretty powerful stuff. The helium nucleus is seen as both regular 4-2 helium, but sometimes you're also going to see that symbol right there, and that's a Greek alpha, all right? So the alpha particle is like this supercharged helium. An alpha particle is oftentimes the product of some of these nuclear reactions, and we'll see it. So again, this is not, the normal birthday helium. This is something to be really careful with. You want to make sure you've got protection if you're around alpha radiation. Similarly to the alpha, there is a beta radiation. Now, normal electrons, we've seen, make chlorine chloride, or they turn the sodium metal into sodium ion, stuff like that. Well, beta particles are like supercharged electrons, and these are also things that you certainly don't want to be messing around with. Lots and lots of energy. Electrons are reactive as they are, so when you make them a beta particle, woohoo, they are super, super powerful. Now, the symbolism, which is going to be helpful to us later on, you can see right there. It's a 0 - 1 E or a 0 - 1 beta. That symbol on the right is a beta representing beta particles. This is kind of interesting. Remember in the type of system we're looking at, the lower left-hand number is number of protons, and the upper left-hand number is protons plus neutrons. When it comes to beta particles, these supercharged electrons, the 0 makes sense because there's no protons or no neutrons. The -1 is a little weird, so bear with me for right now. I'll make sense of this for you here in a little bit. So a beta particle has a 0 - 1 E or 0 - 1 beta. Either one is fine. The next one is a gamma ray, and really this isn't a particle, so that's why I made the kind of silly comment earlier how they're not really radioactive particles. But anyway, gamma is literally gamma radiation. It's pure energy. It's the highest energy found on the electromagnetic spectrum. We talked briefly about gamma radiation in Chem 221. We're going to formalize it. Gamma rays have the little symbol right there, gamma, all right, and that's just like pure energy. Gamma radiation is quite common in these nuclear reactions because there's so much energy. And if energy is released, a lot of times it's gamma. You can also have X-rays, though. X-rays are also common in nuclear reactions, but gamma radiation is the one that's seen most often and the one we'll focus on. Now, in addition to all of these, once in a while, we're going to talk about protons in this section. And a proton can be listed as 1,1p, like the example on the left. And again, that makes sense. Lower left-hand number of protons, which of course is 1. Upper left-hand number, protons plus neutrons, which of course 1 plus 0 is 1, no problem. One proton is also going to be often symbolized as 11H, a hydrogen atom, all right? Because the hydrogen atoms are going to be the protons and stuff, and good to go. In addition to protons, neutrons will also be useful. A symbol for a neutron is 10N. And again, no protons, so that's where the 0 comes from. 1 proton plus neutron in the upper left. Neutron is the symbol, no problem. So protons and neutrons are kind of cool. But the newest one, and the one that really gets me jazzed up here as your Star Trek loving instructor, is a positron. A positron is an anti-electron, all right? So first of all, just look at the symbolism. 0 plus 1 E or 0 plus 1 beta, all right? The regular electron, 0 minus 1 E or 0 minus 1 beta. So they're very similar. There's a reason why the one is negative 1 and the other one is positive 1. An anti-electron is not a proton, which also is positive 1 in the lower part there. So that's why there's a 0. So anyway, these are going to be players. We're going to talk about all of them in more detail, and there is a nuclear chemistry guide in the companion and online that might help you when you go through this section. Let's talk about the anti-electron a little bit more. An anti-electron, which is also known as a positron, is an example of antimatter. Now, if you have been interested in science fiction, antimatter is something that's used quite often. And in Star Trek, my beloved Star Trek, antimatter is what was used to basically fuel the warp engine so they could go long distances and stuff with an antimatter-matter conversion. That's really cool, but actually antimatter is a real substance. So in the upper part of this picture, there's regular matter, a regular hydrogen atom. And normally a regular hydrogen atom would have an electron and a proton. And if you look at the quarks inside, and this is an example of elementary particles, which is a special kind of physics, there's different kinds of quarks inside there, and you can see the little symbols and the colors. Well, antimatter, you would literally have hydrogen atoms. And instead of the electron, you'd have a positron, because a positron is an anti-electron. And instead of a proton, you'd have an antiproton. And you can see inside there, there's antiquarks in the antiproton, making up the anti-hydrogen atom. Whoa. So the theory is, especially if you start dipping into science fiction, is that there could be an exact copy of you, but an antimatter version. And the antimatter version in an antimatter world would have no problems. But if you, the matter version, and your antimatter version of you came together, touching matter and antimatter usually creates a lot of energy. And we'll talk about that here in a little bit. But one thing I do want to point out is that the positron is a true example of antimatter. It's an anti-electron. And positrons are pretty, well, somewhat common anyway, in this nuclear chemistry field.
You're aware that radioactive materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are three different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. We notice immediately that more energy comes from the gamma. One sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away. We notice that the amount of radioactivity is greatly decreased by distance.
This is a pretty cool video, and it shows especially beta and gamma radiation and how it's detected. And they're using a Geiger counter, which is that kind of tube thing there, and the tube has like a detector. It faces the radiation, and each one of the clicks is essentially a radioactive particle interacting with the Geiger counter. So if you have a Geiger counter with those clicks going off, then you know that you've got radiation around. Beta and gamma, as well as alpha, have different properties. Alpha, we saw, was essentially a helium nucleus, so it has mass. It's also the heaviest. Beta is an electron. It has mass, but it has less mass than alpha, so it's maybe a little bit better. Gamma, on the other hand, is pure energy. It's like shining a flashlight, if you will. There's no mass at all. So you can stop alpha and beta radiation pretty well. Like alpha radiation generally is stopped by your clothes, and beta radiation needs something a little bit better, but it's usually by skin, all right? Gamma, on the other hand, is much more difficult to stop. They saw there how the beta radiation was stopped pretty well with lead. Gamma, though, it took a little extra there to kind of kick that down. Distance is another factor, too. If someone was to point one of these radioactive sources at me, intentionally or unintentionally, sometimes the best thing to do literally is just run, because the farther you run, then the more chance the radiation has to interact with something in the air or a wall or whatever, more likely to be stopped. So anyway, it's pretty interesting. We'll talk more about Geiger counters later on, but you can see there are different kinds of radiation, and depending on what kind of radiation you have, there's different ways to stop it.